institution which is holding which is taking care of every kind of organizational problems and expenditure as well.
Great, yeah. So definitely, this is really nice. Yeah.
I don't know. It's time. It's time.
Yes, sir. So can we start?
Yes,
sure.
It is already past 3. Start.
Okay, sir. Thank you. Welcome to all of you.
40 are there. 40 are there. Very good. 40 plus.
Yes, sir.
Good. Good.
Yes,
Good.
sir. So let's start our program. Today I'm very happy to talk to all of you. Today's opportunity to talk here is really a special moment for me, a happy moment for me, because we started our program 2.5 years ago, and as you can see in our poster, it's 50th session of our webinar series. So we can start the session. Respected mentors, teachers, and the dignitaries, ISRO veterans, and experts all over India, and my dear friends, all of you are welcome to UL Space Club webinar session 50. Extremely glad to welcome all of you to the golden ceremony of 50th session of UL Space Club webinar series. And I don't know what to talk about our webinar series, and it's really a special moment for all of us who are working behind this webinar series. And I don't know whether any other group in India has conducted such a long webinar series in India. But it's not just about the numbers, not just about the 50 webinar sessions, but experts from all over India, especially from organizations like ISRO, DRDO, and the institutions under ISRO, VSSC, Satellite Application Center, URO Satellite Center, and many prestigious universities all around the globe, and NITs, IITs, IASC, IAEA, Indian Institute of Astrophysics, and many other experts all over India and all over the globe has interacted with the students of UL Space Club, and many students have nurtured from the environment of this webinar series. This webinar series have nurtured UL Space Club itself, and the students of UL Space Club has got a very nice exposure to the experts and to the field of space science and technology. Today, we have a team of 17 members who is coordinating student members who is coordinating the activities of UL Space Club. 15 of them has been nurtured through the environment of UL Space Club webinar series, and I'm really happy to share that news with all of you. And today, at this 50th webinar session, I want to just share a note about how we started our webinar series. We started our webinar series during the May 2020 when the whole world was stuck during the COVID pandemic situation. We were thinking about a few other programs instead of our space camps. And we started thinking about webinar series, and we thought like we can have 4 to 5 webinar sessions, and let's see what we can do later. Then we got very good response from students and all the experts who supported us. And now we are on the 50th session. Along with this 50th session, we have conducted quiz competitions. After each session of our webinar series, we have conducted a quiz competition related to the topic of webinar session. And we have given prizes for most of the students, and other students will also get prizes. And today also we will have a quiz related to today's topic, and very happy to share that news with you. And today on this 13th of August, we are very close to 15th of August, and we are celebrating the 75 years of independence. We are very happy to celebrate our 50th session on such an occasion. And yesterday was the birth anniversary of Father of Indian Space Program, Dr. Vikram Sarabhai, and UL Space Club also remembered him on his birth anniversary. And I have one more announcement to make to all followers of UL Space Club. We are having a World Space Week celebration on October 4 to 10, 2022, as like in the previous year also. In the previous year also, we have conducted several programs and a special program for school students. This year also, we will having some competitions and other programs. We will announce the details of this program later in the upcoming week. So stay tuned for that. And I don't know what to say. I just asked to one of my friends, Raya, to give me this opportunity to talk here, to tell something about this webinar series, because I personally I'm very happy to welcome all of you to this session. Once again, welcome to UL Space Club webinar session, 50th session, webinar series 50th session. So really happy, and we have few instruction for students. Most of you may know that, and I have to repeat it once again for the newly joined students. So please don't try to switch on your mic and camera during the presentation of our speaker. It may be an interruption for the other students when they are listening to our speaker. And please don't try to share your screen. The speaker will share your screen, his screen when he's taking the session, and don't try to share your screen at that time. It may be an interruption for the students when they are listening, and a streaming is going on through the UL Space Club YouTube channel, and it will be an interruption if you are sharing your screen at that time. So once again, welcome to all, and use the chat window in a good way. We have a chat window in Google Meet. You can ask your questions. You can type your questions there. Our coordinators will collect your questions, and you can ask it directly to the speaker at the time of question and answer session. So once again, welcome, and I would like to invite our mentor and high school teacher, Sajeeth sir, to introduce our speaker. Sajeeth sir, over to you.
A warm good evening to all. Then we are sitting here on the 50th webinar session. That was happened and accidentally happened. And we could say that we are remembering about our constitution and we are celebrating the Azadi Ka Amrit Mahotsav. During these days, we started for that. And we made this constitution for the people and by the people. Likewise, UL Space Club is run by the students and for the students and all the veterans and all the scientists and all the teacher community and the entire society and the social well-wishers are making an umbrella for these students, and we are proud of them that they are emerged a lot of their qualities by organizing these things. Good organizers, good managers, and they have developed their own vision about their future also. That kind of an environment that we are creating here by running, or that we are enjoying as mentors for these students. We have students from the 5th grade to the UG students here, and the supporters also. So that's happy, and now we could say that we have done halfway for our students making this environment, and our next aim to make familiarize this situation, this umbrella of US Space Club to the all students under a vision of STEM, science, technology, engineering, mathematics. That is the basis of very science, and to make curious about the science, that we have arranged a Skywatch session under the guidance of Surendran Punashiri sir, and we are doing it in the Sky Safari program, and students are the curiosity is the basic element that require for a student to become a great scientist or some more that we are expecting here. And we have today a great speaker from a great institute, and we are proud that he is from our place also, and Dr. Ninan Sajeeth Philip. And I could see Dr. Nikhil Mukund also there, who introduced these great scientists to us, and he's joined with from Germany, and he's the great scientist of India, and we are proud of him, sir. And along with that, let me introduce Dr. Ninan Sajeeth Philip for our students to know his profile. He's a person with versatile field. It's not a particular one. He's a person from biology. He's a person from astrophysics and all. He's an all-rounder. He's a real role model for our students or the science enthusiasts. That's the things. And presently, he's a adjunct professor in artificial intelligence in Applied Medical Science, Department of Medical Research, Believers Church Medical College, Tiruvalla. And he's a visiting professor, Ayuka, Pune. And he's a reader, approved research grade, Mahatma Gandhi University, Kottayam. And he's with research collaborations with visiting associate of Inter-University Center for Astronomy and Astrophysics, Pune, and Cardiff University Then on LIGO gravity, the detection project, I think the Nikhil Mugid is also working there, and astronomy department in the Arizona State University, and African Institute of Mathematical Science, Caltech and Harvard and Cape Town. That was for all developing machine learning tools for big data, and have collaborative research publication with Illinois and State University and Monash University, etc. So it's a global citizen that we have today, and he's with an industry experience as Dean and Director of Artificial Intelligence Research and Intelligence Systems, Aries Lab, in his own village. That's the main thing. In the prominent newspapers, that news has come 1 year back, that we are proud of him, sir. And then he's in technical expertise in these areas, development of machine learning methods of domain name generated sites for tracking possible malicious sites. I think that's about the cyber, other kind of atrocities, and search about that. And development of deep learning model for removing atmospheric blur produced in ground-based telescope imaging. Then expertise in OS level debugging system and analysis to write and understand debug assembly level of codes of IBM PCs and OS level module in Linux. Software development in Python, Perl, C++, C, Pascal and Fortran for scientific applications, and PHP, MySQL and Apache for web-based applications. Development of machine learning tools that operate on huge volumes of data generated by astronomy, observatories and biological sciences. Development of natural language processing (NLP) tools to extract insight from documents, feedback, comments and medical transcriptions. Development of tools for future identification for classification data sparse environment. Development of non-invasive machine learning tools for studying biodiversity, habitat and species behavior in natural environment. Development of machine learning tools for automated identification of species using underwater surveillance camera video shootings. And he is engaged interested in development of deep learning tools for automated particle picking in cryo-electron microscopy, that's MRC, images and similar image segmentation and classification tasks, and development of high performance computing environment for massively parallel processing. And now he is engaged with all these areas with the artificial intelligence application in the fields of biology, physics, astrophysics, every areas. And his major research areas in astronomy research, star galaxy classification, galaxy morphology classification, transient identification and classification, anomalies and glitches detection in gravitational wave detectors, X-ray astronomy of active galactic nuclei and black hole acceleration disks. Then he is interested in climatic research, climate forecasting, trend analysis and weather prediction using machine learning tools on archival and real-time data. Then natural language processing, text processing, summarization, insights, keyword for identification, context and sentimental analysis using existing and explanatory entropy-based methods. And he is interested in the research of image processing, automated detection of protein molecules, cryo-electron microscope images for protein structure determination, detection, tracking and behavior pattern identification and classification of species using understand these things. Then is also very close with the biodiversity research, monitoring and analysis of after effects of Kerala flood from selected. This is a contemporary study from his part and it's done in Kutanad, and is developer for Porteus Atma. It's also an open software system of Linux OS have supporting system. He has developed an Atma software for this Linux platform, and another development of Atma Ubuntu. It's a Ubuntu version of Atma, and he has done wonderful publications. That is a very inspiring thing for our students. More than he started this publication in 2002, and still it's continued. More than 20 to 30 publication has come in prominent journals, including the Nature. And it's a great experience for our students, and it's an inspiring personality come here on our 50th webinar series of UL Space Club. So we make a warm welcome to our chief guest, Dr. Ninan. Along with him, we welcome all the veteran scientists like PJ Bhatt sir, Rangarajan sir, Jairam sir, and our founder and mentor E.K. Kuti sir, and Dr. Nikhil Mukund, and all other veteran scientists, and our students who are the enthusiasts and the real recipients of this program. And I welcome all of you once again on behalf of UL Space Club, and invite Dr. Ninan Sajeeth Philip to this platform. Welcome, sir.
Thank you very much. Shall I share my screen?
Sure, sir. Sure, sir. Then our program is being live streaming in our US Space Club YouTube channel. That also noted here. Welcome, sir. Continue, please.
Yeah. So I hope that my screen is visible.
Yes, sir. It is visible.
Good afternoon. I wish to thank all of you. There are a lot of great people there, of course, and especially Shajil, who has been very kind in reminding me several times not to forget this, and has been inviting me for this meeting, which made this opportunity for me to meet with all of you. I understand that this is a 50th talk you are having in the series of talks you are having every month. And in today's talk, I do not want to take you to any big scientific details, but would like to tell you a story. The story about our nearest star, which is the sun. I don't have time to tell you the complete story. So towards the end of the talk, I'll try to give you some references from which you can read and complete the story and know much more, as much as we know today about the star, the sun. So, as all of you know, our nearest star is Sun, and this is the only star we have in our solar system. It is a hot ball of gas, mostly composed of hydrogen and helium. Although all of you know these things, I just want to consider the young aspirant minds which are also there, the students who would like to clarify some of the things. That's why I'm explaining these things. Apart from hydrogen and helium, it also has some lighter elements like calcium, some fragments of iron, etc. Now, the size of the sun is huge. How huge it is? Well, I'm showing here a picture in which you can see the planets. You can see in the planets line, the third one is our Earth. And you can see part of the sun on the left-hand side, because I cannot have space to draw them to scale. In fact, 98% of the solar system, the mass of the solar system, belongs to sun. And it is so huge also that the size itself is very large, that you can place 110 Earths across it. I'll show another picture in which I'll explain that. So the image shows the relative size of the planets in our solar system. The two giant planets that you see are Jupiter and Saturn, and they are also mostly composed of hydrogen and helium. Of course, Saturn has a core, which is a very solid core, mostly of iron and other materials. The two blue planets that you see are Uranus and Neptune, the bigger planets. Both have a lot of water and methane, which gives them the particular blue color. Our tiny Earth, as I mentioned, is the third in the line of planets, and also is a blue planet in our solar system. In fact, the two neighbor planets we had also is believed to have some past which was very much like ours. But they do not have a magnetic field. I'll come to that, why magnetic field is important, which caused them to become desert-like. Okay. So you all have at least must have seen solar eclipse at least once or twice. May not be a full solar eclipse, partial solar eclipse. In the total solar eclipse, the moon covers the sun completely. And that happens when it is exactly before or exactly in line with the Earth and the sun. The shadow on the moon at that time, the shadow of the moon on Earth at that time will cause something like darkness on the surface of Earth. And that is visible at about a radius of about 90 or a distance of about 92 miles, which is about 148 kilometers. To 148 kilometers means slightly less than the distance from Calicut to Cochin, which is about 180 kilometers. In the rest of the Earth, it will be only partial solar eclipse. And it takes moon about, I must say how fast the moon is moving. The moon is moving at about a speed of about 3,700 kilometers an hour. So that is the speed with which moon is moving. Your car is moving at a speed of about 70 kilometers or 80 kilometers per hour. Whereas moon is moving with an average speed of about 3,700 kilometers an hour. So with that speed, it takes 1.5 hours for the moon to cross or transit the sun. Meaning that even if the moon is moving at that speed, the size of sun, which is at a very far distance, it is just like a small ball there at that distance, but it takes that much time for the moon to cross it. So that gives us some idea about the size of the sun. If we know the size of moon, we can, of course, if we know the distance to sun also, we can, of course, find out the size of sun based on this, because this is plain trigonometry. Now, to give a better picture of the size of sun, can you see a dark spot in that sun which is pointed by the arrow? That is the size of our big Earth compared to the size of sun. In fact, you will need 110 Earths lined up along a line to cross the diameter of sun. So that huge is the size of sun. And when I talk about the size of sun, it is not fair unless I refer it to something else. What is that something else? This is our Milky Way galaxy. And this Milky Way galaxy has 2 billion stars similar to our star, sun. And most of them are of the size of the sun, and some of them are as much as 100 times bigger than sun. That's the maximum size to which a star can be. And some of them are about 8% that of the size of sun. That's the minimum size a star can have. Because a star has to be producing its own energy to nuclear reaction, and that's the minimum size required for gravity to produce such an effect. So our sun is sitting in one of the spiral arms of this galaxy towards the edge. And it is not even of the size to be pointed as a spot there, because it is very small compared to the size of the galaxy and also compared to some of the big stars, giant stars we have. And so tiny is our solar system. Yet we think that we are masters of the universe. That's the irony here. And very likely that's a false pretension. This universe is much, much complex and bigger than what we can imagine or what we have already imagined. So these are just some facts about our sun. Most of you know these things, but just for completeness. In terms of energy, for example, USA is one of the nations that rank top in energy consumption. Still, energy produced by sun in 1 second is enough to meet all the needs of US energy for 90,000 years. That is the estimate. So that is a huge amount of energy that sun produces. And the sun has been here for about 5 billion years burning like this. And it is expected to go for another 5 billion years before it becomes a red giant and finally as a white dwarf. So it has been a great puzzle. What powers the sun at this much of, and to give out this much of energy and to live for this much of long time? And of course, it was only about 100 years or a little more than that, since we realized that this energy is provided by the nuclear reaction in which hydrogen molecules combine together to form helium and release energy. And this release of energy is what powers the sun. So if you look at the center of the sun, the center core where the nuclear reaction takes place is really hot at about 15 million degrees centigrade. But its surface, outer surface, is relatively cool and is at about, say, 6,000 or 5,000 or 6,000 degrees centigrade, which is what emits a white light which we receive from the sun. There is nuclear reaction taking place, which means that nuclear explosions are taking place at the center of the sun. There are two things that binds the sun in its shape, although these explosions are taking place. One is gravity, which is a major force. And the other one which holds them together is a magnetic field, which we'll come to later. So to see the different parts of the sun, astronomers look at the sun in different wavelengths. You know that X-rays, you take the X-ray to see the bones when it is broken. You know that X-rays can go deep inside the objects, most of the obstacles that visual life have. X-rays are also emitted by the sun, and being exposed to X-rays can cause cancer and even kill some the living organisms. Luckily, the outermost atmosphere of Earth do not allow X-rays to pass through. Otherwise, we would have not have been alive here. No life would have been possible on Earth. So we have an atmosphere which protects us from these X-ray radiations, even from ultraviolet radiations, you know, about the ozone layer and all those things. So to see the sun in X-ray, we need to send satellites which go beyond the Earth's atmosphere. And in this picture, we see the sun as it looks through an X-ray eye. So you see so many black regions there, we'll come to that. You see so much of burning ink happening there, we'll explain all those things. One thing you must have been told in your, whenever there is a solar eclipse, you are always told not to look at the sun during a solar eclipse. Why? Have you ever thought why? What is the problem in looking at the sun when it is covered by moon? There is no sun there. Why? Well, you know, you are told that you will go blind. And in fact, you will go blind if you look at the sun when it is sitting behind the moon. Ancient people thought that sun god is so angry when we watch it being swallowed by a big snake, and that anger makes us blind. But we know today that that is not the reason. The exact reason is, in solar eclipse, moon covers only the region from where white light comes to us, which is the only light we can see. But light has a very vast range of wavelengths, and we see only a very small portion of it. The other things we can't see. But there is an outer atmosphere for the sun called the corona that is about 2 million degrees in temperature as compared to the 6,000 degree which we see. And what happens there? Because you know that the temperature and the light that it produces is proportional. If you try to heat something up in the flame, you'll see that initially it becomes red, and when it becomes very hot, it becomes white. And if it is still heated and if it takes up heat, then it can start emitting other radiations like ultraviolet radiations, which are not visible, but they can pass through. And at this high temperature, most of the light produced would be ultraviolet, which will come, and because we do not see them, they will pass through our eyes. When the bright sunlight is there, our eyelids will close just to reduce the amount of light cooling. When you do not see anything, just like in darkness, your iris will be wide open, and this ultraviolet radiations will come in and will damage your eyes. And it's only for the past few years we are able to understand how this high temperature comes in the coronal region. It's a pumping mechanism, or the details of which I do not want to go into, but it comes from the sun itself and it remains there, heating up the atmosphere there to this high temperature. So this is something that causes damage to our eyes if we look at the sun during a solar eclipse. So what keeps the surface temperature of sun a constant is the same mechanism that keeps boiling water at a constant temperature of 100 degrees centigrade. When water boils in a vessel, you can see the water from the lower layer rising up, where it is heated at the bottom, rising up, moving to the upper layer, replacing or pushing down the upper layer downwards, which goes in circles. And as soon as it comes in contact with air, it releases the energy, and some other layer comes in, hot air layer comes in, pushes it down, and this process continues. And this process is called the convection current. You have studied in school. It is this convection current that helps water to maintain its temperature, boiling temperature at 100 degrees centigrade, when the atmospheric pressure is something like 76 centimeters of mercury. You can think of the sun as a huge vessel that is heated at its center, and the hot gas that surrounds moves out, heating all the inner layers and moving out to the surface. As soon as they reach the surface, they will have some temperature of 5,000 to 6,000 degrees centigrade. And when they reach the surface, there is nothing above it, so it releases the energy, radiates out the energy, cools down, and then moves down. So this process of convection current is what keeps the temperature constant there. And if the temperature was not constant at 5,000 degrees, as we see here, we would not have been able to live here. Even slight changes in temperature, when this surface gets disturbed due to, we'll come to that, sunspot effects, we find it very inconvenient to live on this planet Earth because it becomes really hot. So what I want to remind you is that the physics that is going on here is a simple physics you have in your kitchen where you boil water. It's a heat exchange that's taking place through this convection that maintains the constant temperature of the surface of the sun and the constant temperature it gives out through the entire process. Although the internal reactions are very producing a very high temperature and very massive explosions, we see a quiet, very pleasant sun just because of this convection current. Well, everything is not that quiet about the sun. Like the boiling water in the vessel, the surface of the sun is also experiencing very high turbulence like bursts and solar quakes, similar to earthquakes. The picture shows some examples of explosions seen on the surface of sun. So there is prominence, there are other entities which you see there. Again, we won't go into the details. You can find all these details in the links that I'll provide at the end. So to study the sun and to closely observe the sun, European Space Agency and the NASA together, the US NASA, together launched a satellite in 1995, and it is able to observe the sun continuously for 24 hours a day. A normal satellite usually goes around the Earth, which means that half of the time it will be behind the Earth and it won't be able to see the sun. So to see the sun 24 hours without any discontinuity, SOHO has to be, SOHO is the name of the satellite. SOHO had to be placed at some location between Earth and sun. And you know that gravity is the force that binds the sun and Earth together, all the planets in the orbit. So you can find out points where you can find out the gravity at any point as the difference between the pulling force to a sun and the pulling force to a planet. That is how the moon goes around Earth. Now, there are points in between the sun and the Earth where gravity cancels each other. You need to consider those points by considering all the planets and all and also the sun. And these points are called Lagrange points, where these forces cancel each other. And SOHO is put in one of these Lagrange points so that it can always look at the sun. And of course, it will have a rotation on its own axis. I mean, a rotation above the Lagrange point, but will always be pointing towards the sun, like this. And can do observation 24 hours a day, continuously. Why continuously? Because we want to study the details about the sun. The sun itself is rotating, and we need to be observing it continuously. And SOHO has several instruments built into it. Again, we will not go into the details, but we'll show you some of the instruments. And all these instruments are built in, which are continuously observing the sun and are sending these details to us. And all these details are available online. You can find the pictures, a picture of the sun today, or since its launch in 1995. So that is available online, which I would like you to go and take a look. So these are some of the instruments that are there. Let's move on. And in this talk, as I said, I'm just giving you a story. So I'll be telling you some of the instances in scientific discoveries that has taken place. And one of this is very interesting because there is an instrument called SWAN on the SOHO telescope, which was able to look at the arrival of the comet Halley. And this picture was taken in 1997. You can see some blue rings there. They are in fact clouds of hydrogen, which are accompanying the Halley comet as it arrives. This is the Halley-Bopp comet. It is about the size of these rings. The outer ring is about 70 times the size of the sun. 70 times. We have been talking about the big sun, and now we are seeing a big cloud of hydrogen around the Halley comet. And to give you the proper understanding, there is a dot at the right-hand side corner. You can see that, which is representing the sun. So that is the size of the sun compared to this blob of, or this very big packet of hydrogen, huge cloud of hydrogen that has been observed by the SWAN instrument in the SOHO telescope when Halley's comet was coming. So this changes our notion that space is empty. Space is not empty. We often think that outside the Earth's atmosphere, the space is empty. Space is not empty. It has a lot of hydrogen, although at very low pressure and temperature. Whenever gravity gathers them together, they club together. And it is the same process that made this sun come into existence. All the stars came into existence after what has happened, which we call the Big Bang or whatever. Now, sun is such a hydrogen ball, but the size here is much bigger than 70 times is the size. Why is not becoming a star? It's not becoming a star because the density is much lower. In the sun, the density of hydrogen is much lower. It's much more hydrogen than what this 70 times more hydrogen is, because it is at a lower density. So more than the size, it is the density of the hydrogen caused by the gravity pressure. That is what causing hydrogen to get converted into helium through nuclear reaction at the core of this gravitating ball of hydrogen, which is the sun. And this picture is also taken by one of the instruments in Soho. So this is showing the Doppler effect. You know what the Doppler effect is, right? If you do not remember, I'll just tell you an example. Suppose you are standing on the railway station platform and a train is whistling and moving through the station. As the train is approaching you, the pitch seems to be much higher, and as the train is moving away from you, the pitch lowers. That means you feel that there is a change in sound, but there is no change in sound. It's the same sound. When it's arriving towards you, the pitch increases, and when it is moving away from you, the pitch decreases. And this is what is called Doppler effect. This same effect can be observed even when a vehicle is moving close by, a car is moving with, or some vehicle is moving with a music instrument on it, and you listen to the music. As soon as the car is coming towards you, you feel that the music is played at a higher speed, and as the car moves away, you feel that the music is just dragging up, something like that. So this is what we call Doppler effect. And this can be used to find out the rotation of sun. So we want this a spherical ball. And how will you find out in which direction it is rotating? See, when it is rotating like this part is moving towards you and this part is moving away from you. It's rotating at a certain speed. Well, so this part should be like the car that is coming towards you, or the horn that is being blown when it is coming towards you. And this part is moving away, which is on the opposite side. So this part should appear, if it is red, it should appear more yellowish, and this part should become more darker, which means that the wavelength increases, or it becomes more dark red color, and this side, which is moving towards you, becomes brighter, which tends to make it yellowish color. So you can see that same effect here, which tells you that the sun is in fact rotating in which direction? It's rotating in this direction. Okay, this direction when I show you, but it may appear, meaning that the yellow side is coming towards you. That is what you need to understand. The yellow side is coming towards you, and the black side that you see is moving away from you. So it is rotating. In this picture, it is rotating from right to left. That is a better way to say. It is rotating from right to left because right side is much brighter and the left side is going much darker. So that is another instrument, the Doppler effect, that can be determined. So these are the things we are observing by observing the sun closely. Okay, there is another device, another camera called the EIT camera, which is able to look at the sun in different wavelengths, particular wavelengths. There are what is called filters, which will allow you to see the sun in different wavelengths. All the wavelengths being emitted from sun, covering from X-ray to ultraviolet or even to infrared. If there will not be an infrared light, but all the light that is coming from the sun can be observed with this kind of filters. So by observing why you use different filters? Because you want to see different depths. You know that the X-rays can go much deeper, and X-ray emissions are coming from much deep inside the sun. So it's coming out from there, so you'll be able to see what is happening in the interior. And on the photosphere, which is the bright side, which is the sun you usually see when you look at the sun, the white bright region, that is emitting at a wavelength of something like 600. It's at a wavelength different. It's a wavelength in which the white light we observe from the sun is seen, but it's at a temperature of something like 6,000 degrees centigrade, and that light is coming. So we can use filters to see different regions of the sun, and those filters can be implemented in the EIT camera instrument that the sun has, that the SOHO has. So SOHO will observe sun in different bands, and this is a combined image created by that EIT instrument by looking at the 3 different bands of the wavelength coming from the sun. Okay. For example, you can see an eruption observed by SOHO in this image, and this EIT image was taken in 1997. And you see the eruptions that are happening, which are just like fire coming out of a torch or something like that. So it's burning out, and those can be seen at different wavelengths because some of them may not be visible to the naked eye, but can be seen in X-rays or some other band or ultraviolet radiations. And the mass that is also emitted with it, sometimes they come back, sometimes they come to us also, towards Earth. That we'll also explain. So one of the puzzles that existed from the time Galileo, who first discovered these dark spots on the surface of sun called sunspots, was the way in which they are created. How are they created? When SOHO looked through using their EIT camera at the sun, they did not appear as dark as we see them with our naked eyes while looking at the sun. In fact, they looked very bright, and they could also see a lot of matter coming out of it. To give you an analogy, you might have observed in your kitchen the pressure cooker, when it is becoming hot, start emitting gas outwards and producing a whistling sound. And as soon as one whistle is made, it stops. It waits for some time, it produces another whistle. Why there is a delay? See, as soon as this gas is emitted out, that reduces the temperature inside because it is emitted out at a high pressure. It is going out, energy is going out. So that cools down the pressure cooker. Again, because you're heating it, it will rise in temperature, reach a particular level where the pressure becomes sufficient to blow the whistle. It will again blow the whistle and send out some gas from it or hot air from it, and cools down again. Likewise, when hot matter from the sun escapes, sorry.
No, the percentage is visible. It's visible. It's visible. Yeah.
Okay. Please let me know if you find any difficulty in. Okay. Likewise, when the hot matter from the sun escapes from the convection surface, which is where this whole convection mechanism keeps its temperature the same, when matter escapes from there, it cools down that region. And that is what we observe as dark in the visible region, in the visible light. But whatever is coming out at very high temperature, and they may be emitting ultraviolet radiations and also X-rays, which will be visible only in X-ray cameras. They won't be visible to the naked eye. So we see them as black spots. And you must have observed that when there are a lot of black spots on the surface of sun, which is called the sunspots, when sunspots are large in number, the hotter it is. Because all these radiations are coming out. And they are coming towards us, some of them, not all of them. Some of them are coming towards us. And that makes the sun, that makes the atmosphere around the sun hot, and also these hot particles coming towards us makes us feel hot. So even with this small change in the surface, the balance in the surface temperature, we find it very difficult to manage. Which is why we say that if there was no convection current, or if there was no stability in the temperature of the sun, life would not have been possible. Well, now a great question remained. It is, we know that the sun is just like a bomb or a cracker, which is bursting. It's uncontrolled reaction that is taking place, nuclear reaction that is taking place. And what is holding it together? There is a lot of pressure to go out, even breaking gravity, which is holding it together. Of course, gravity will pull them back as soon as they go out. But still, what is maintaining them in the ship? We came to realize that sun also, it is in fact the magnetic field that sun has. We knew that sun must be having a magnetic field because at a high temperature, you know that everything is in the plasma state. Plasma state means electrons and protons are separated. They're in ionic form. So if the sun is, if they are moving inside, they should produce a magnetic field. And we knew that sun must be having a magnetic field. And this magnetic field is in fact holding the plasma together. Otherwise, in this burst, they would have at least partially escaped the gravity and came out. So whatever matter that is ejected from the sun is pulled back both by gravity and is streamlined back to the surface of sun by the magnetic field, by what you see as loops there. These are magnetic loops. So you know that charged particles moves parallel to the magnetic field. So as soon as there is a loop, the charged particle which is escaping will move back to the surface of the sun itself. So that is what is doing it. But one question remains. What is that question? Why there should be loops? How come that the sun's magnetic field have loops? On Earth we have magnetic field, but we know that it is from north to south. There are no loops. So this is the other instrument, so as it is a magnetogram. It takes magnetogram recordings of the sun and shows you where the magnetic fields are. So you can see a black and white spot on the surface wherever there is this sunspot. They actually show the north and south poles of the magnetic field. So the loop is there. That's how we realize that there are loops. Now the only question that remains is, how are these loops formed? Which is not found on Earth. You can also guess how they are formed, but I'll answer. What is the difference between Earth and the sun? Earth is a solid, rigid body. So when Earth rotates, all parts of it rotates along the same axis together. Otherwise, I could have gone to America very easily. Just need to wait till America comes or me, just walk in. That's not possible because America will remain at the location where it is, at the latitude and longitude of the Earth, and India will remain at a particular latitude and longitude region. So for the Earth, all parts move with the same speed together because it is a rigid body. But what is the sun? Sun is a gas ball. It's a ball of gas. If you try to make a whirlpool in water, you find that the different parts of water moves at a different speed. It's not with the same speed they move. If you put a piece of paper inside, you see that at some regions it moves faster, at some regions it moves slow. It's not moving with the same speed. Likewise, different parts of the sun moves with different speeds as it rotates about its own axis. It takes some 27 days for it to go around round. So in this time, different parts will move with different velocities.
Stop, please stop.
Yes. Yeah. Can you hear? Hello.
Yes, sir. It's audible.
Okay. Since all matter in the sun is in the plasma state, they are all charged particles moving in different speeds. So you have charged particles moving in different speed at different positions. When charged particles move, you know that they produce magnetic field. And there is a problem with magnetic field. Magnetic fields cannot touch each other. Those that come close to each other diverge out because they do not want to touch each other. And this forms, when they diverge out, they need to join somewhere. This forms loops on the surface. So that is how these loops are formed. Wherever these magnetic fields come together and try to touch each other, they instead go out and fall apart. So that is how these loops are formed. And this making and breaking of loops happen in a period of about 11 to 12 years in the case of sun. And that is why we have solar cycle. You must remember these sunspots are visible, they disappear for some time, they come again. And this happens with a period of about 11 to 12 years. So this is the periodicity in which we see the sunspots. And sorry, though the sun is very huge in size, because it takes only 27 days, Earth days, when we look from here, to go around its axis, is moving at a very high speed. And in this image, you can see from these regions, some matter is being emitted continuously, which are the bright things that you see there. And these are called flares. So solar flares are very common, and they are seen to be coming out from these sunspots. So I mentioned about solar cycle, and that is a period of activity of the sun. The period from where it is very quiet, silent, to a period when it is very active. The duration is about, between two periods is about 12 years or something like that. 11 to 12 years, it varies slightly. And we have been observing this for several hundred years now. Ever since Galileo discovered sunspots, we have been observing it. And it has been systematically observed by many for at least the past 100 years or more. So in this diagram, you can see how the sunspots varied for the 100 years, past 100 years, starting from 1900. And you can see the 11-year period. The 11-year periodicity very clearly here. Sorry. So that is where all these bright regions are coming. And this is an EIT image, again from the Soho. Its EIT imaging camera has taken this image in 1996 and also in 1999. You can see that in 1996, the sun is very quiet. There are very few sunspots or no sunspots at all. But by the time it was taken in 1999, it's completely ruptured. The surface is completely ruptured, and there are a lot of flares coming out, and there are large sunspots on it. How large these sunspots could be? Here is a comparison. So you can see the size of Earth, it's drawn to scale. And you see that that's a small sunspot. In fact, there are bigger sunspots. This sunspot can easily swallow our Earth. The Earth can easily pass through that. And in some cases, the sunspots could be so big that more than one Earth can simultaneously go in. So that is the size of the sunspots that we see, the ruptures that we see on the surface of sun. And when this happens, a lot of matter comes out. And here you can see what is called a prominence, where matter goes out and falls back onto the surface of the sun through a loop that is produced on the surface of the sun. So this kind of activity can be continuously seen by SOHO and can predict if there is a disaster. What kind of disaster can come? If the magnetic field breaks off, matter will come out, and that will come straight towards us because of the force. It's coming out with high pressure, so it will come out. It will escape gravity and come out. And some of those matter can reach Earth. Some of them can fall on our satellites and can damage them. So SOHO also has a protection mechanism. If some matter is coming towards it, as soon as it sees it, it just goes into its cavity, protecting itself from the whole blow of matter from the sun. And this matter emission is generally called the coronal mass emission or CME emission from the star. And CME emission has some effect on Earth also, that we'll also find as we move along. So it is at this place where you find those rings are coming and ending at the surface of Earth, the sunspots are seen. So those are the regions which appear as black. So now astronomers give different names to these loops seen. And this naming is mostly based on their nature, how big they are, how prominent they are. So they are called prominence. And what amount of matter that comes out of it. And this picture was recorded by SOHO in 1997, where you can see a large loop is formed. If you take Earth, you can take and put 28 Earth-sized objects between those regions. So that's huge it is. And if this loop break off, that will allow matter to come out of it. So through these loops, of course, matter is moving, and matter is in the plasma state, which means charged particles are moving. And if it breaks out, as I said, it will come straight towards us, and that is what we call the coronal mass emission or the CME. And when that breaking happens, just like we have earthquakes, a lot of solar quakes happen. And this picture shows you a solar quake that happened and has been observed by SOHO. So you can see how it is formed and how it propagates through the surface of sun. Now, these pictures indicate, in fact, gives a much more clearer visual effect on CME emission, coronal mass emission. And these were recorded in 1998. The dark circle that you see at the center is a mask, just put in front of the camera to mask the sun from allowing it to send it light rays on us. One of the interesting things in space is that if you place something before a star or a sun or the sun, if it is just in front of it, it can completely obscure the light coming from this particular object in front of it from reaching your camera. But on the surface of Earth, it is not possible because you have the atmosphere which scatters light and it will come from all directions. But outside, because the density of the gas, which is hydrogen, which is very small, you find that if you place something, the scattering is so low that you will be able to see even the stars at daytime. That's how SOHO is able to, you can see so many spots there, they are stars in the background of the sun. So even at time, SOHO is able to see the stars and even satellites moving around. Satellite means if there are these comets moving around the sun, even at daytime, even when the sun is burning with its full brightness in front of it. So by keeping this mask in front of the camera, we are able to see the CME emissions coming out from the sun. And this also reminds you about the pressure cooker example that I mentioned before. Just like from the pressure cooker, the gas emits in all directions. It's emitting out. And there are videos of this available on the Soho website, which I will mention later. You can look at it, and it's really fascinating to watch them. And these emissions, in fact, go to the end of the solar system. So in between, they pass our Earth also. So on the way, as they pass our Earth, it could have been very catastrophic. The winds are so strong that they can easily blow out the atmosphere of Earth or any planet. And that's how the atmosphere of Venus and Mars got so thinned down. Luckily for Earth, we also have a magnetic field which they don't have. And this magnetic field, as you know, magnetic field will force the charged particles to move along it. And that means when there is a magnetic field like this, it will have some effect on the, see, these charged particles are moving, they are coming. So one magnetic field will have an effect. The charged particles, magnetic field by the charged particles will have some effect on the Earth's magnetic field, which distorts it. And as shown here, it will distort it like this, making it a tail-like structure. And because of that, what happens is that along the tail, because magnetic fields never interact each other, touch each other, along the field, it will drive all the matter, charged particles coming to move away from Earth. So it's just like a streamlined boat that moves through water. It just lets all the charged particles move through its sides, protecting the Earth and its atmosphere. It's a miracle. We do not know. But if that was not the case, we would not have been alive here. We would not have had any atmosphere to live. So it is only because the Earth has a magnetic field, it shields us from heating the atmosphere. And these charged particles move to the end of the solar system, just like a wind. And this is called a solar wind. However, since the magnetic lines comes and hits the north and south pole of Earth, at these poles you can see some lighting effect when these charged particles arrive. And these beautiful, colorful lights patterns that are seen are called aurora lights, which are just because of the solar wind, the charged particles hitting at the top. And apart from this lighting effect, and from protecting the magnetic field, these charged particles which are coming are believed to recharge the Earth's magnetic field also. So this periodic recharging maintains the atmosphere of Earth, protects the atmosphere of Earth. They show us some lighting effects and they just pass off. And that is required, this recharging is required for prolonged protection of life on Earth. So this is very interesting and this is very fascinating. And I do not want to, I can keep on saying many things about the sun because much of it has been known because of the explorations done by Soho. But I'll just take you to the website and would suggest you to read. So this is the Soho website. So I'll concluding my talk with this Soho website. You can find more and useful information. Even as I said, today's information about the sun. And there is a classroom there where you can find most of the slides I have taken from there. All these slides you can find there. And also you can find very useful class teaching methods there, which will teach you how the sun keeps us safe, provides us energy, and makes it possible for life to continue on this planet. There are also several educational programs that NASA and this Soho website provides. These links are also available at the website. I would suggest you to go and take a look at them. So thank you for your patient listening. You can, of course, write to me, or you can visit our website. And you're most welcome to ask questions even now. Thank you.
Exploration to our nearest star. Really, sun is a very known factor to us, but it's a real unknown factor to the students also, and even for the teachers and the total community. Because we've been discussing about the sun, and now we focus on James Webb Telescope and all other things beyond these things. And it's a wonderful world you created, and it was systematically and it was arranged very academically very well as a leadership project process in your presentation. It is highly appreciated, sir. And you started from the beginning, and you end with a good opening for the student to explore themselves through the websites and all of the resources. That way we expect from you, sir, and we are so blessed, and our students are so blessed. And I think they are with some curious question to interact with you. And before we leading to there, I think our Kuti sir will mention few more things before our student starts. Welcome, sir.
Thank you, Shajil Mash. Actually, I must first thank Shajil for organizing today's talk by his good contact with Dr. Ninan Sajeeth Philip. And we have had few talks in related area, but in this area, we are very, very thrillingly listening to the story. So I don't know how to thank Dr. Ninan Philip for spending good amount of time. 1 hour. 1 hour is spent with us today, this afternoon, giving everyone a widespread exposure. And a person with lots of publications, making a colorful, beautiful story on our nearest star, Sun. Spinning up a new horizon for our students, opening up new resources for them, and we are extremely happy to have spent a very wise afternoon today with Dr. Ninan Philip. I don't want to come between students. Students must be eager to ask several questions. Varun and his team must be ready. And we have also got exceptionally good scientists present like Nikhil Mukund, Rangarajan, PJ Pat, etc. Here. And they may also like to interact. So let us proceed for our usual question and answer session. Thank you very much once again to our exceptionally good speaker. Thank you.
Thank you.
At the outset, let me convey my heartfelt thanks to Dr. Ninan. It has been a very informative session, sir. So much of information, because we feel we know something little bit about sun, but what we know is nothing. And every time it is so, it is going to be so even after 50 years. I know that. But the amount of information you have gathered, I mean, you have given us today, I think it is really, I was not aware of many of those things, like how the actually solar flares happen, solar wind, the way in which the sun, many things. And we had heard about Soho mission. We know that Soho mission has given us so much of knowledge about sun, but today you have opened up the gates and told us what way it is. Of course, I'm sure what you have told is there is much more to tell. I know that, as you rightly told. And I am sure on 2025 onwards, we are going to have much more knowledge with Solar Parker Pro, because 2025 it will go, I think, somewhere around 9 to 10 solar radii distance from sun that is there. And maybe to small extent, our ISRO mission, Aditya L1, also will give some contribution from India towards this. Thank you, Ninan sir. Thank you so much. I mean, it has been excellent.
Thank you, sir.
On sun, especially on SOHO missions findings. Thank you.
Thank you.
Hi, can you hear me?
Yes, we can. We can.
Okay. Yeah, thanks a lot, Sajeeth sir, for coming to this session and giving us this very nice talk. And it's always like a refresher course, because we think we see sun every day. We think we know about it. It's like not. We think it's not not a great thing to search more. It's complete, but he has told us like how complex it is, and then how many there are a lot of open questions just about the sun, and then we are having a lot of missions like SOHO and Aditya that's coming up from India to learn more about the sun. And and as he said, like it was just like, to me also it was just like a story. The way he presented was very nice, and as he said, like space is not really empty, and it was very nice. And I would also like to thank Space Club for hosting him and giving us this opportunity. And it's very nice to know that they are celebrating 50th iteration. And I hope they have many more talks from eminent personalities like him. And personally, Sajeeth sir has been my mentor, I would like to say, for like last few years. And as Sajeeth sir has said, like he has a very wide interest, right here. So he and his student, like Dr. Shilo Abraham, they taught me machine learning, like at least a couple of years back. And it has been a nice journey interacting with him and learning more about various topics. So I'm always thankful to him. And I just wanted to say that the first machine learning algorithm that I used in my research was the difference boosting neural network algorithm that he had developed, I think, like decade back. And then it really was one of the first works in the LIGO collaboration, which was successfully able to differentiate black hole signals and transient glitch events. So we can see how ahead he was in terms of his vision and research, and I would always be grateful to him. And I don't want to take too much time, so thanks again for giving us this nice talk. And let me hand over to Sajeeth sir.
Varun? Shreya, it's a net issue.
So, am I audible? Yeah. So it's time for the question and answer session. You can unmute your mics and ask your queries.
Shreya, this is Shreya, our one of the very senior student leader.
Hi, Shreya.
Good evening. Harpreet, you can ask.
Somehow the satellite is protected from the sun's radiation.
Yes, the satellites, in fact, SOHO will send out alarms. It will take a few days for the radiation to reach, light itself takes 8 minutes for it to reach Earth from the sun. So maybe 2-3 days it takes for the matter to come from sun to earth, even if it is moving at very high speed. So within that time, there will be alarms sent to all the satellites, which will protect the solar panels, which is the most delicate thing. Without it, it won't be able to function at all. It will fold down its panels and keep them safe. The SOHO itself does that, and it communicates to other satellites, which also replicates the same thing, so that they are protected from this blast coming out. So this was something that was affecting our earlier satellites very much. As soon as they go on board, they may get hit by something. There are other things which can come and damage the satellite, but this is one of the common things, because these are charged particles. When charged particles are coming in, they will cause high fluctuations in the electric current, because they can move through the conductors in it and will damage many of the electronic devices. That things are protected now with the help of SOHO.
Thank you, sir.
Is there any other questions? If you're facing, yes, Prabita, go on.
So you had said that magnetic fields, they don't attract with each other, right? They do repel. So is there a science behind it on why they do repel, why they don't come together? Or is it just like that, a fact?
It's a fact. It's a fact. It's very difficult to answer why they should not come together. Magnetic lines of force never intersect each other. That is something we know. And the magnetic field, how they are formed, we know how they are formed, because there is very well understood electromagnetic theories that define it. But why they do not interact each other? Because they cannot touch each other. They repel each other when they are in the field, because field lines never usually intersect each other. So that is an observed fact here.
North and South Pole, like, opposite poles attract, and, like.
Poles will attract and like poles will repel, and but what I'm talking about is the field, the magnetic field that is drawn from the North Pole to the South Pole. They never intersect each other.
Yeah, thank you, sir.
Prabita, before you leaving, please introduce yourself. We want to hear who you are from.
Oh yeah, so my name is not actually Pravita, it's my mother's ID. I'm Yutika Magesh, and I'm in 9th grade. I'm studying Global English School. I'm really keenly interested in this field of astronomy and astrophysics, and I would like to know many things. And currently, I'm more into the general theory of relativity and trying to focus more into that.
Okay, definitely you can associate with the UL Space Club, and then you can log on to the UL Space Club website and contact us. Okay.
Yes, sir.
Then, you are from exactly your place?
I'm from Calicut.
Okay, no problem. Okay. Then is there Shreya? Is there any other?
Yes, sir. Leela is facing an issue with the network. Okay. She asked Parker Solar Probe by NASA how it is protecting itself from sun's denser and hotter atmosphere. Harpreet, can you please mute your mic?
Okay, so I didn't fully understand the question. The question is how SOHO is protecting itself from the heat of the sun?
Yes, sir. Parker Solar Probe by NASA, how it is protecting itself from.
Okay. See, all these solar probes, if they reach beyond a certain region, they will get damaged. So you can shield them. You can shield them with various protective materials, which are developed for shielding them. And this shield is what helps them to keep themselves safe from the heat of the sun. But of course, there is a limit to which this shielding can be done. And that is the closest we can move to the sun without getting burned. But all other probes which go into the sun, they burn. They burn at the end of the journey.
Okay, so she also asked, can you please explain the term Lagrange point?
Okay, so Lagrange point is say, suppose you have two gravitating or two objects which are experiencing forces, 2 points from where an object is experiencing force. When the forces are in equal magnitude, it will be in equilibrium. It will be just like having no force. So suppose you have a force, there is a sun here, there is a earth here, and you can find a point which will be close to earth because sun is much more massive, where the force of attraction due to earth and the force of attraction due to sun both cancel each other. Very simply saying, that is where you call it a Lagrangian point. But both of them are moving, so these points will be, of course, be moving around the sun as we move. But this particular point is where the gravitational forces will be. Very simplistically saying, that is a point where these forces will be equal. And the Lagrangian point is a mathematical concept. It can be between any two forces where they bring in equilibrium. Why we have satellites going around the Earth? Because the Earth's centripetal force cancels with the force of gravity. So that is why satellite which is moving at a higher level needs to move only at a slower speed. And that is the reason why all the geostationary satellites are moving are placed at a very high orbit, because they should move along with the Earth so that they will always be at the same location from the Earth. If the satellite at a lower position, they'll have to move faster so that they may not fall out. Because the gravitational force is higher, the centripetal force has to be that much higher to cancel each other. So that is basically the concept of Lagrangian force, Lagrangian point. And there will be L1, L2 points like that, which will be places where you can find this kind of activity, which are the details into which I do not go.
Okay, is there any more questions?
I think Nila was there, I think. Shreya, just check whether Nila is there. I understand she was.
Nila, can you speak up?
Am I audible? Clearly?
Yeah, you are.
I am Nila KS. I'm a 10th grade student from Government Girls Higher Secondary School, Cherthala, Alapura. I was a part of the space camp that was happened at the May 23rd to 25th.
Okay. Shreya, I think the questions are over, and I will get some few more reflection from Mr. Chandrasekharan sir. Chandrasekharan sir is from Wayanad. He is continuing supporting our students. Welcome, sir.
Sir, I really enjoyed the presentation, sir.
Okay.
Oh, okay. Thank you.
Okay. Then we have Dr. Srikumar from University of Calicut, Department of Life Science. Is there with us. Srikumar sir, could you
Yes,
mention a
sir.
few words? Welcome, sir. Welcome.
Yes, wonderful. I listened to most of the talk, but intermittently I got interrupted because of the internet.
Okay.
Wonderful, sir. Wonderful presentation, Dr. Ninan, Sajeeth. I really enjoyed. Thank you very much.
Thank you.
Thank you, sir, for your presence with us. Thank you. Yeah, that's why we are mentioning. Then I think we are going to a conclusion. Jaram sir told me he's engaged with the former deputy.
Sajeeth,
welcome,
thank
sir.
you.
Welcome, sir. Welcome, sir.
So, Ajit sir, you're telling a story. You said no. Actually, indeed, it was a very beautiful story about our own nearest star, and of course, sun is the very sustainer of our own existence on this beautiful earth. So the story was well told. About our sun, many things that we know partially, but details we never wanted to know, or we were not too busy looking at that. But you explained it, the composition, activity, structures, what goes in, and the probes and the exploratory part of it. No? I think it was very, very beneficial. And the most wonderful thing is that you explained it in very, very common man's language so that everybody could grasp it. Thank you very much. I benefited a lot, actually.
Thank you, Jairam sir. And we have a Deputy Director from Education Department, Government of Kerala, Diba ma'am. Please, Diba ma'am, are you here? Diba ma'am? Oh, I think, okay, I think his son is there. Okay, then I think she is not available now. And Varun, you can come with
Sir,
your quiz and
Nigel Mohan sir is there. Sir,
who is?
sir, would you like to add some points?
To whom? Varun, you are asking? Nigel Bose sir already mentioned everything.
Okay, sir,
Whom you are asking, Varun?
I was just logged out from due to my network
Okay, no
issues
problem, no
here.
problem. You continue with the
Okay,
quiz.
sir.
You
Sir,
see.
before going to the conclusion, I have a request to all supporters of your space for dearest members. I request all of you to turn on camera, and I request Sriram for taking a screenshot of this ceremony, because as it is our 50th session of our webinar series. So I request every support and members of your space club to switch on the camera. Sriram?
This just 1 second, Varun. This is, as you mentioned, it's a 50th session, and we have started it on 23rd May 2020. During the epidemic time of 2020, it was a weekly program every Saturday. But when schools started activating themselves in classes, 2021 January onwards, it has turned out to be a monthly session. We have been continuing it. In addition, we have had, I think, 16 or 17 special sessions, isn't it, Varun? In addition to this, isn't
Yes,
it?
sir. Yes, sir.
Yeah,
Yes,
yeah.
sir.
So this we call it webinar. Others are special occasion like Moon Day, International Space Week, and things like that. So it has been a very, very nice thing to recall that we have been able to. It's made possible by commitment, dedication, and interest in us by various speakers, including today's Dr. Ninan. Thank you.
Varun, the vote of thanks.
Sriram, are you able to take it? Sriram?
Where is Sriram? Sriram?
Then I think
Any problem for Sriram?
I think I could do that. Then I will
Okay,
increase.
Okay, sir. Thanks.
Yes, I'll the 42. Please open your. Okay, all of you, please switch on your camera.
All of you can switch on your camera.
Yes, please switch on your camera. All of you. Then only few I could see there. We have only yes. Please for a few moments. Please switch on your camera. All of you, please. 1 second, 1 minute, only 1 minute. We require your presence, and I could see only few. That's why, and we can adjust this. Okay. Then I am taking that. Okay. Thank you all. Thank you.
Thank you, sir. So let's move on to the conclusion. So before moving on to the conclusion, like I said, stay tuned for the updates from UL Space Club, because next week onwards we will have updates regarding the programs which will be held in connection with UL Space Club webinar, Space Week celebrations and our Foundation Day celebrations. Our UL Space Club activities were started at 2016 Space Camp, which was organized under the leadership of Kudisa at ULCC Cyber Park. And as a memory of that, October 8, we are going to celebrate it as a Foundation Day. And we have the Foundation Day celebrations and Space Week celebrations ahead. As part of that, we have planned a competition for students. Stay tuned for the updates. We will give you the updates through our social media channels, and we have several WhatsApp groups and email broadcasts of the participants who are following UL Space Club. So we will share you the details as soon as possible. We will give you the quiz link as soon as possible through the today's quiz link will be given to all of you through our channels, WhatsApp group channels and social media channels also. It will be published. So you can access the quiz just after the vote of thanks. It will be active only after the vote of thanks, and you can access the quiz at that time. And the quickest answers and accurate answers will be considered for the prizes. And the prizes are sponsored by our supporter, Sinabay Nature. So that's it. I would like to welcome Shreya to express word of thanks.
As already mentioned, we had our 15th session of our webinar series, and we all are so glad that we had a great speaker, Dr. Ninan sir, with us on this special occasion. And I would like to thank Ninan sir for being a part of our program. Thank you, sir. And as well as I would like to thank all our mentors, Kutti sir, Shajil sir, Jairam sir, and all our well-wishers for being our constant support. Without your support, we couldn't make this. So, thank you to all. And I would like to thank each and every person who gathered here for their active participation. So, thank you.
Okay, then thank you, Ninan sir, and Kuti sir, Nikhil Mugund, and PJ Bhatt sir. And we are waiting
sir,
for.
I have an unofficial announcement.
Okay, before okay. Then we have coming programs. World Space Week is coming, and I think some people that will get some clarification from Varun.
So no, sir, not related to Space Week celebration. We were planning to launch a podcast and media platform by UL Space Club students, which will be on the basis of podcasters related to space science and technology, and also UL Space Club programs. And also, we are seeing it as an opportunity to interact with more experts, like conducting interviews, panel discussions, and such things through that platform. So we invite a good name for our podcast and media platform. We are inviting good suggestions for naming our podcast and media platform. I request all our participants and mentors to suggest us a good name for our podcast and media platform. That's a request. So I request all of you to help support us.
Okay, Varun, we are concluding these things. And Kuti sir, anything more to be added, sir? Kuti sir?
No, nothing more. I think it is covered very well. Everything is covered very well, so nicely.
So we have celebrated. Yes, sir. Yes, sir. Thank you. Then we have celebrated the 50th edition of our webinar, and it's a continuous support, and we have created a good environment for our students under the blessing of these great scientists of India. And we request Ninan Sajeeth Phillips sir to continue his support to this forum of the Science Forum of Environment, and we'll see soon with more programs in the next month. Thank you all.
Sure, I am very much impressed by the program that you are conducting, and I'll surely be with you.
Thank you, sir. That's the word we are.
Thank you, sir. Thank you very much. So nice. So nice.
Bye.
Bye.
Okay, to suggest a name for a podcast session, you can mail to